Swayam Prabha. Digital India. Educated India.
Okay, so now let's come to the other problem that we encounter in practice, which is the classification problem. Now here you are given an image and you want to classify it into one of k classes. In this case, k is equal to 4. So for the given image, I want to say whether it's an apple or a mango or an orange or a banana. Is that okay? Fine. So now, what is the loss function that we'll use here? Can you use the squared error loss function here? What is 0, 1 loss function?
If the input is correct, then there is no loss. If the output is incorrect, then there
Is it a smooth function? Is it a differentiable function? No. We want functions which are why? Why do you want differentiable functions? Because then we can compute the gradients and then only we can apply gradient descent. Is that fine? Okay? With the squared error loss function. Yeah, so why not use the squared error loss function? What's wrong with that? You could actually use the squared error loss function. There's nothing wrong with that. But in this special case, when you have the classification problem, and in particular when you want to predict one of k classes, okay, there's something better that you can do. So squared error loss is a valid loss function to use, but there's a better loss function that you could use. So can you tell me what it would be? First tell me what is the output function that you'll use here. So softmax. What is softmax? Sigmoid. Can I use the sigmoid function here? Yes or no?
We could use the sigmoid function and then scale it up as probability, that is an apple with probability so much, mango with the probability so much.
So you'll use 4 sigmoid functions. And suppose these 4 sigmoid functions give you output as 0.4, 0.4, 0.4, 0.4. Is it a probability distribution? What's the condition for a probability distribution? Sum should be 1. So if you use independent sigmoids, there's no guarantee that the sum will be 1. So he had a nice way of thinking about it, that my outputs are between 0 and 1. I have to either say it's a 0 or I have to say 1. Sigmoid is a function which gives me values between 0 to 1. So why don't I use just 4 sigmoid functions? All of these will give me values between 0 to 1, and I could treat them as probabilities. But where was the flaw in that reasoning? The sum will not be equal to 1. So that's why good that we know what's the wrong answer. The wrong answer is sigmoid. You cannot use the sigmoid function. Can you use the linear function, which we used for regression? Yes, no, maybe. Can we use the linear function? Yeah. No, I mean in the second part, can you use the linear function? In the first part, we'll use the linear function. Again, what would happen? What is the output that we want between 0 to 1? The linear function can give us any outputs, right? There's no restriction on that. Fine? So then what do we need? So notice that the input is a probability distribution. Now why am I saying, sorry, y is a probability distribution. And this is the y which I've shown you there, right? Y is equal to 1, 0, 0, 0. What do I mean by y is a probability distribution? What is the meaning of a probability distribution? Is this a discrete distribution or a continuous distribution? Discrete. Everyone agrees with that. Now what do I mean when I say I'm giving you a probability distribution? Suppose there are 4 outcomes. There are 4 outcomes in this case, right? Apple, mango, orange, banana. If I ask you to give me a probability distribution, what am I asking you to give me? Probabilities of each of these outcomes, right? Have I given you the probabilities of each of these outcomes here? Yes or no? Remember, in the training data, I'll give you xi comma yi, and my yi here has 4 components. In this specific case, the 4 components are 1, 0, 0, 0. Now I'm asking you, have I given you a probability distribution or not? Yes? What's the probability distribution? All the probability masses on apple, all the other elements have 0. Is that fine? So even a certain event can be represented as a probability distribution. So if I say that there's a probability 1 of something happening, all I'm telling you is that the probability of this thing happening is 1, of everything else happening is 0. And that's exactly what happens when I give you an image. If I give you an apple image, then with probability 1, this is an apple, and with probability 0, it is any of the other classes. Does that make sense? So what I'm giving you as y is a probability distribution. So if your true y is a probability distribution, what should your predicted y be? It should also be a... That makes sense? If your true guy is a probability distribution, it does not make sense to predict something which is not a probability distribution, right? So you should try to have an output function which gives us a probability distribution. Does everyone agree with that? Okay. Now, having 4 independent sigmoids, does that give us a probability distribution? Yes, no. If I have 4 independent sigmoids, what's the problematic word in the statement which I'm saying? Independent, right? If I have 4 independent sigmoid functions, I cannot be sure that I'm going to get a probability distribution. So I have to do something so that these outputs are dependent on each other such that I get a probability distribution. Now, for getting a probability distribution, what are the 2 conditions that I need to have? Sum should be 1. Everyone should be greater than 0 and greater than or equal to 0 and less than or equal to 1, right? Is that fine? So I need a function which ensures these things to me. Now, do you know a function which does this? So all of you said that a linear function will not work because it will not give me outputs between 0 to 1. Okay. Let me try to counter that. Yeah. So let me try to counter that. Suppose I tell you that in my data, I had seen apples 4 times, mangoes 10 times, oranges 6 times, and bananas 10 times. Now, if I ask you the probability of each of these things, how will you compute that? Sum of all of them, and so the numerator would be each of these frequency counts, and the denominator would be sum of all of them. So I had numbers which were not in the range of 0 to 1, but I could convert them to 0 to 1, right? So then why couldn't I use the linear layer? I could have chosen the linear layer just as I chose in the regression problem and then done what? So let's try to understand the question which I'm asking, okay? So what I'm saying is, I'm talking about the output layer, okay? Is that fine? So now this is my A and this is my O. I'll just call it as H for consistency, right? So these are my light green guys, which are the A's. And I've already computed A. How did I compute A? A was again B plus W into H2, right? The previous guy. Is that okay? Fine. So now what is A? A is a vector. So it has A1, A2, A3, and A4. And from here, I want to go to an H. This is my final output, H1, H2, H3, H4. And what do I want this output to be? I want this output to be a dash. A probability distribution. That's what we have been talking about for the last 5 minutes. Okay. Now, I gave you an example where these values were 10, 4, 6, 16. And then you gave me a way of converting this to a probability distribution. So why couldn't you have done something similar here? What would have been the equivalent of that in this case? H1 is equal to A1 by summation of AIs. Is that okay? Everyone fine with that? H2 is equal to A2. Okay. So if I do this, I'll know that the sum is going to lie between us. The sum is going to be 1. That's trivial. Am I guaranteed of the second condition which I wanted? will all the values be positive? Yes? No, right? Because AI came from this formula. Where does this formula say that it will produce only positive values? It could produce negative values also, right? Then you'll have a negative quantity divided by a sum, which would be, it could be negative. Does that make sense? So you'll end up with negative probability values. Is that fine? No, right? So that's why you cannot do this simple normalization. So then what do? You could do square, that is one thing. So what we do in practice is instead of using this, A1 over summation AI, we use something known as the softmax function, which is e raised to A1 divided by, summation e raised to AI. How does this help? How does this help? First of all, is the summation going to be 1? Right? I'll have e raised to A1 plus e raised to A2 plus e raised to A3 plus e raised to A4 divided by the same thing. So that's going to be 1. Are all quantities going to be positive? Yes or no? E raised to anything is going to be positive. Right? So I've taken care of both the things. Right? So this function is known as the softmax function. Okay? So remember, my h is actually a function of A. Okay, my final output, that is y hat, which I'm calling as h, is a function of A, and this is how I write the function. So now let's understand the dimensions again. What's the dimension of A? How many elements does A have? K. How many elements does h have? K. So when I say h is a function of A, I need to tell you how each element of h is related to each element of A. Okay? And that's what I have told you, that hi, the ith element of A, h is equal to e raised to ai Does everyone get this? Okay? So this is the softmax function. And it makes sure that our output is a probability distribution, and it makes sure that the output sums to 1 and all the elements are greater than 0. Is everyone absolutely clear with this? Please raise your hands if you did not understand this. How many of you understood this? Please raise your hands. Up and high. Okay. So we started with this thing that, first of all, we noticed that even though I'm given the label as y is equal to apple, I can actually write it as a probability distribution. I can say it's actually the distribution of a certain event, where the event is that the outcome is an apple and everything else is 0. So all the probability lies on the event that the outcome is an apple. Okay? And now since my output, true output, is a probability distribution, I make sure that my predicted output is also a probability distribution. And we came up with certain choices. So we said linear will not work because the sum will not be between 0 to 1. For that matter, even the individual elements may not be between 0 to 1, right? You can get negative values also. Then we thought, okay, we'll take 4 sigmoid values. They'll all be between 0 to 1. But even that had problems because the summation will not be 1. So then we finally came up with this softmax function, which ensures that each of the elements is greater than 0, and the sum is up to 1 because we are doing this normalization, right? So that's what the softmax function is. And this is exactly the y hat L which I have written there, or y hat J which I have written that, is exactly the formula which I wrote on the notepad earlier, okay? So this is called the softmax function. Now let's look at the following. Our true output is a probability distribution. Our predicted output is also a probability distribution. Now I want to capture the deviation between these two probability distributions. One thing is you could use the softmax function. So let's see, you could use the squared error loss function. So let's see what that means. This is what your true output looks like. Y is 1, 0, 0, 0. And suppose you predicted y hat as 0.71, 0.1, 0.15, and 0.05. Okay? Now what would the squared error loss do? .1 minus 0 the whole square plus 0.15 minus 0 the whole square and plus 0.05 minus 0 the whole square. So this is fine, right? Because I'm predicting certain values which are off from the actual values, And this is one way of capturing the difference between the true values and the predicted values. Is that fine? So you can use the squared error loss. But when we are dealing with two probability distributions, and if I want to see how different one distribution is from the other, is there something else that I can use? Is anything else from probability theory that you know of that you can use to capture the deviation between two probability distributions? So in that case, I don't think I can go all the way back up to expectation and start from there. That will itself take 3-4 hours to do. So what I'll do is I'll just give you the formula. You can go back and look up what cross entropy means. There's a Wikipedia page for it. You can start from there and then look at some other reference material for that. So for now, I'll just tell you what the formula is, right? And I'll try to give you an intuitive explanation for the formula. So what cross entropy does is summation I is equal to 1 to k, okay? The true, or let me just use the index C because that's what maybe I is okay. Okay. This is what the formula for cross entropy is. So instead of minimizing the squared error difference between the two predicted vectors, you can think of these two as probability distributions and principally arrive at something known as cross entropy and compute the cross entropy between these two distributions. And this is what the cross entropy formula tells you, right? So there are 4 terms here, okay? In the summation, there are k terms, or in our case, k is equal to 4. And you'll take the true value of yi and the predicted value of yi. So in this case, how many elements would remain in the sum? For our classification problem, where k is equal to 4, how many elements will remain in this sum? 1, right? Because it's yi log yi hat, and only one of the yi's is going to be 1, because all the probability mass is on one event, everything else is 0. So if I expand this formula for this case, then it's going to be 1 into log of 0.7 plus 0 into log of 0.1 plus 0 into log of 0.15 plus 0 into log of 0.05, right? And so all these 3 terms will disappear and only one term will remain. Is that fine? Does that make sense? Okay. And for any training example, the same thing is going to happen. Either it's going to be an apple or a banana or a mango or a watermelon. So only one of these 4 terms will remain and everything else will disappear. Okay. And which is the term which actually remains? The term which remains is minus log of which y hat? The y hat for which I is equal to the true class, right? So the y hat of the true class. In this case, the true class was apple. In some other case, it would be banana. In some other case, it could be mango. Okay. Now, what is y hat c actually? So in this case, this was y hat c. What is it actually? The predicted probability of the correct class. The predicted probability of the true class. So what am I trying to effectively do this? I'm actually trying to minimize this quantity. So let's understand how we have arrived here. So we wanted to minimize the cross entropy, which was given by this formula. But we observed that for any training instance, only one term in this formula is going to be active. Everything else will go to 0. And which was that term? It was the log of the probability of the correct class. Okay? Now I'm trying to minimize this quantity, which is the same as maximizing. It is the same as maximizing what? Minimizing the minus of something is the same as maximizing that something, right? So it's the same as maximizing log of y hat c. So what am I trying to do in effect? I'm trying to maximize the probability of the correct class. Does everyone get that? I know that in my training data, all the probability mass is focused on the true class, right? So that's what I'm exactly trying to achieve by the objective function, that even during prediction, all the probability mass should be focused on the true class. Is that fine? I'm trying to maximize the probability of the true class. How many of you get that? Please raise your hands up and high. Okay, good. So instead of this, you can use the cross entropy function, and only one term is going to be active, which is the term corresponding to the true class. And in effect, what you're doing is you're maximizing the probability of the true class. Is that okay? Fine. So that's fine. So what you have seen is two kinds of problems. One was regression, the other was classification. In the case of regression, our outputs were real values. And in the case of classification, our outputs were probability distributions. So what was the objective function that we chose for regression? The output function that we chose for regression? Linear. And what was the loss function? Squared error loss. Okay. And what was the output function for the classification case? Softmax. And the loss function? Cross entropy. Is that fine? Okay. And just remember, if you got confused with the whole cross entropy bit, first, know that instead of cross entropy, it's okay, although not advisable, to use the squared error loss. Second, the cross entropy loss just boils down to minimizing the cross entropy, just boils down to maximizing the probability of the predicted class. Or rather, maximizing the predicted probability of the true class. Is that fine? Okay? Okay. So these two loss functions and these two output functions take care of a large number of problems that you will deal with while you're practicing machine learning. And all these problems fall under the umbrella of regression or classification, right? So if your problem is of regression, you can use linear output with a squared error loss. If your problem is classification, you can use the softmax output with the cross entropy loss. Is that fine? So we'll end here. So we'll meet again after the break.